Welcome. My name is Jeremy Stieglitz, and I am the Principal Product Manager for AWS's Key Management Service. Today, I'm going to be talking about data protection strategies for the cloud and really drilling into KMS and our overall architectural approach for key management, as well as key encryption and data encryption in AWS. Along the way, we'll look at a brief overview of the design of KMS, and then we'll talk about some best practices in how to build systems for performance, protection, and policy management. And we'll put some tips and guidance around some new features that have launched in KMS to help you achieve those. Why use data protection on AWS? In general, I think there's two top-level reasons customers come to the cloud looking for data protection. One is the obvious one. They're bringing valuable assets, valuable data into the cloud, and they want to ensure the protection of that data. The protection of that data is meaningful as an investment. It could be patents, it could be pharmaceutical research, it could be customer data. They also want to protect themselves. Customers that operate in the cloud need to have a trustworthy brand to their customers. Data that leaks, data that gets breached requires businesses to publish notifications and inform their customers, and that can be damaging to a customer's trustworthiness and their trusted brand in the marketplace. But data protection can also do other things in the cloud. It can unlock data for faster agility. It can provide you with tools for automation and moving faster in cloud workloads. But the second sort of fundamental driver for data protection is that many of our customers are required to do so. There are privacy rules and regulations globally, some at the state level, some at the regional level, some at the federal and country level, some as large as the European Union level for data privacy and the protection of sensitive information. There's also industry-specific regulations. The credit card industry has a well-known set of compliance standards known as the PCI standards for the proper protection of credit card data. So our customers really have both these goals in mind. The sensitive data they want to make sure stays locked in the cloud, and they have data governed by regulatory, privacy, and security standards and audits, and they need to show compliance against those. Let's take a look at how we achieve that in the cloud next. We build cryptographic tools across every component at AWS, from the way we connect our data centers together at layer 1 with fiber optic encryption in the cabling of our data networks, right up through this OSI model at layer 2, technologies for MACsec, at layer 3 and 4, transport, VPN, IPsec, and TLS technologies for building secure tunneling and secure session communications. We are a leader in TLS technologies, and we have advanced toolkits for building your own S2M. And we have academic research in next-generation cryptography to develop approaches for post-quantum cryptography and crypto agility so that you can use both ciphers of today and protection for cryptographic implementations in a post-quantum world. I'm going to be talking today primarily about the top of this stack, which generally we refer to as data at rest. This isn't data moving around in networks or moving in fiber optic cables. This is data that you write to storage. Maybe you're writing EBS storage. Maybe you're writing files to S3. Maybe you're building analytic workloads that use Elastic MapReduce or Kinesis. Maybe you're writing next generation applications that use microservice architectures, Kubernetes or Lambda. In all of those instances, all of those services have mechanisms to provide data protection for any of your data that you store inside the cloud. And we'll be looking at KMS as an architectural building block for that data protection. How do we map this data encryption at AWS? Well, in some ways, it might be easier to map the tools that you can't support data encryption with. Starting in 2020, AWS set a goal that any service that handles customer data must provide an option to integrate with KMS to manage data keys and provide scalable data protection in that service. As a result, over 103 services today support data encryption with integration to KMS. It might be easier to list the services that don't support encryption. All of the usual top-level services that you rely on: S3, EBS, EC2, Nitro, Lambda, Kinesis, Secrets Manager, CloudTrail, WorkDocs, etc., Aurora, RDS, Mongo, DocumentDB, all of our major database engines, all of our microservices and Kubernetes platforms all support data encryption. But we've got another 30 in the pipeline. And so by the end of this year, as we launch new services, you'll see that number continue to grow as AWS scales out new innovations. The terms I'm going to be using today are fairly well understood in cryptography, but I just wanted to spend a moment and highlight them. I've got a slide coming up on envelope encryption. It is the most important thing to learn from today's presentation, is why we use envelope encryption, how it works, and how it scales out data protection at AWS. It is the primary way that KMS operates to provide key management services to your data in the cloud. The meaningful part of an envelope is the KMS key that encrypts keys to create the envelope. And we'll be talking about that in our next slide as well. When most people think about cryptography and encryption, they generally think about the data key. For me, I'll call that the working key. That's the key that actually locks your data. So when you bring a patent to S3, the data key is the key that is used to encrypt that patent. Your patent is the plaintext. That is the data you present to be encrypted. It is fully readable. It exists in a PDF or doc or JPEG or any other format. And when we use encryption, the resulting file will refer to as ciphertext. I'll also use the words locked data. Ciphertext is transformed data run through an encryption algorithm. One of the easy rules at AWS is that we don't use a lot of different types of encryption algorithms. We have standardized on AES, which is the NIST-approved symmetric cipher, generally for data protection. We use AES in a mode called Galois counter mode, the shorthand of which is AES GCM. It's a nice version of AES that gives us some authenticated data validation, and we use AES at a key size of 256 bits. That's a rather large key for AES, but we do so because it gives us some forward protection. In the future, we have to think about different types of cryptographic analysis, and one of those involves the use of quantum computing. And AES 256 has some interesting protective properties going into the future. A quantum computer in its best design would weaken an AES key by the square root of the size of that key. So in short, an AES key today, well into the future, would still provide 128 bits of strength, even in a post-quantum world. So AES 256 is a nice protective boundary and a nice long-term key size to use and anchor our protection underneath. I mentioned this notion of an encryption envelope, and I mentioned this notion that once you understand this pattern, you'll understand data protection in all of our services. So let's spend some time here and walk through how an envelope works and why it's important. And for my example, I'll use S3. S3 is our #1 driver of traffic to KMS. It is the place where people use the most encryption in AWS. And so in this example, we can think of this as an object in S3. This is that patent that I mentioned, or that pharmaceutical research data, or automotive customer purchasing data. It's your sensitive data, and it's in its plain text format, and you want to bring it into a protected format in the cloud. So you use the S3 put operation, which will place this data into an S3 bucket. If you've configured this for data protection, S3 will need to encrypt it. And the way it will do that is it will ask a data key of KMS. It will send an API request to KMS and say, I need a data key. And S3 will use that data key to transform that patent data or that customer data into ciphertext data. But if that was the job, it would be all done. Data key, data, ciphertext data, it's protected. But what do you do with the data key? How do you open this again later on? And that's where the key envelope comes in. In addition to giving S3 the data key to encrypt data, KMS also gives S3 an enveloped version of the data key, which is in ciphertext format. And S3 will store these together, the ciphertext version of the file and an envelope of the data key to open that file. And that's all S3 needs to store. Notice that everything that S3 stores is ciphertext. An envelope kept in KMS generated the data key and encrypted the data key and sent it back to S3 to attach to this object. Of course, where did this envelope key come from and how is it protected? And that's the fundamental purpose of KMS. KMS creates, protects, and manages envelope keys. The shorthand for these we call KMS keys. KMS keys also need protection. How do we protect those? We use keys, of course. We encrypt all customers' KMS keys with what we'll call domain keys. These keys are housed in our FIPS 140-2 security level 2 HSMs. And these keys are operated only in our HSMs. And that is essentially the operation of KMS. It creates keys in these hardware security modules. It protects their operation inside these HSMs. And it hands out data keys and ciphertext envelopes of those data keys for your data protection across AWS. So what this looks like is a very repeatable pattern. When objects or data gets placed into any of our services, they all need data keys to protect those objects. And they get those data keys from KMS. And they name a customer's key as the enveloping key that should envelope those keys. And that's essentially it. They use a data key to create ciphertext, and they wrap next to it an envelope of that key, protected by a KMS key. All KMS keys are protected inside our fleet of HSMs. And so the security of all these distributed systems is anchored by very high security of our fleet of HSMs in these systems. And that's my overview for KMS. We have a lot more reference material at the end that I will provide in the end of my presentation for you to learn more about the operation of KMS. One of the most important questions we get asked, of course, is can AWS see my keys? Remember, we have large customers bringing very important data to us. So they want to reason about what are the controls we've put in place so that AWS can't use my keys on their behalf. We have important security controls and third-party attestation and evidence of the security of this system. Keys never exist in plain text. In fact, we've never seen a key. We've never read a key. We've never exported a key. We've never needed to access a key in plain text. A KMS key gets created within the boundaries of our HSM and immediately encrypted. It is only ever decrypted inside the boundary of an HSM, never viewable to humans, and only decrypted by a customer's request on a customer API with customer rules and roles governing the use of that key. Our systems, when operational, have no human access whatsoever. There is no operator access to our HSMs. The only thing that can call our HSMs is the KMS application sending in those requests authorized by you. In fact, our HSMs themselves cannot be updated. There is no running config changes. There is no human ways to interact with these systems. You must take these systems offline, and every key in the system will be zeroed out when you take these systems offline to make them upgradable. So after a reboot, all HSMs are in a non-operational state. They have no key material in them. And software can only be updated after multiple AWS employees have reviewed the code under a quorum of multiple KMS operators with valid credentials. We bring a lot of these controls through an auditing process called SOC. I would refer you to the AWS Artifacts tool to gain more evidence and more third-party attestations around the controls we've put in place to verify that our ability to access your keys is zero. And some of this is evidenced by SOC Control 4.5. Customer master keys used for these cryptographic operations are logically secured so that no AWS employee can gain access to the key material. That concludes my summary for an overview of KMS. Now I'd like to jump into those 3 parts of best practices for operating data protection in the cloud. And to do so, we're really going to look at 3 different types of guidance. We're going to start with some protection tips, better ways to think about protecting your data in AWS and some configuration choices you have. And then we'll look at some performance tips for large-scale applications and large workloads. And then we'll finish with some best practices and least privilege and policy control to more narrowly and with more granularity control who and how and when and under what conditions someone can access a key. I think sometimes people over-focus on cryptography, and they ask a lot of questions about key sizes and ciphers and key material and hardware security modules, and they miss the important aspects of authentication and authorization. You must get both right. We believe we've built a system that helps you do both. But we'll spend some time here looking at policy because it's as important. It makes no sense building a very strong lock and then letting everyone know the combination to that lock. And that's really what we hope to achieve with better policy controls, the very tight, specific, granular ways to control who and when a key gets used. In terms of protection best practices, I'd like to take a quick look at 5 today. We're going to talk about the different types of keys that you can elect to use. We're going to take a brief look at key rotation. We'll make an example out of encryption context, which is an important authorization anchor that you can add to your data. And then we'll look at confidential computing with a capability in Nitro enclaves. And then we'll talk about different backends that you can use to keep KMS keys. We have different support for different options, and we'll look at all of those options in terms of where you store keys in KMS. Let's jump in. So KMS offers 3 different types of keys, and they're really on a scale of the most control by you and the most control by AWS. So a customer managed key is fully yours. You create it, you delete it, you set the life cycle of it, you own the policy of it, you own the activity on that key. Any activity on that key reports into your customer CloudTrail. You determine whether you want to rotate that key, and you determine whether you want to make that key available in other regions through a feature we launched last year called multi-region keys, where you can elect for a key to be copied and replicated to other regions. These keys bill at $1 per key per month, and they give you the most control. On the far right, we have kind of the opposite kind of key. If you want AWS to just take care of everything for you, you can elect to use an AWS-owned key. This is a key created by the service. It is a key owned in the service account, not in your account. This is a key with policies created and managed by the service team. In fact, you can't see the key policy for this key. It is managed by the service and owned by the service. And this is a key with no sort of audit trail or activity reporting into your CloudTrail. It's essentially a way to say, AWS, take care of everything for me. Just make encryption by default. Our AWS owned keys rotate. We actually recently changed this. They rotate now on a fixed yearly basis. And in only very certain narrow circumstances can an AWS key be copied to other regions. There are about 3 or 4 services out of the 103 that have very specific reasons where they need the same key material in multiple regions. But as a general rule, our security best practice is that all services should be strictly region isolated. And for that reason, our default position on AWS-owned keys is that they aren't copied to other regions. So this is a yes, but it's only in very limited services like WAF and IAM Federate that there are very narrow use cases where a key is copied. These keys are free to use and free to store. There are no charges attached to you in any way, shape, or form for this easy button, let AWS take care of it for you. You'll see in the middle a bit of a hybrid approach. An AWS managed key is kind of a hybrid. It's a key owned in your account, but AWS takes care of the policy for you. You see activities on this key, but each service makes a decision on whether to rotate or not. These keys are never copied to other regions, and you do not get charged for the storage of this key. But API calls that use these keys will bill your account on API usage. So this is a bit of a blended approach, sort of halfway between AWS owning everything and halfway between you owning everything. I think from a security, flexibility, and policy control standpoint, I would start with customer managed keys. They give you the most flexibility. There's also the question of where to store keys. KMS offers some different options for storing them in the fleet of HSMs that I mentioned, or using your own HSM to replace our fleet of HSMs. This is called the custom key store, and it allows you to isolate keys in your own customer-owned and operated HSM called the AWS Cloud HSM. Another option is to import keys that you create somewhere else. In this flow, you generate the key material somewhere outside of AWS, and you send that key material into AWS KMS through our import API. The import API will also place these keys into our HSM. However, they will be placed into a reduced redundancy domain. So in essence, we're sort of leasing your keys. We're leasing your keys so that we can use them within the cloud, but you are the ultimate creator and owner of those keys, and you are responsible for the durability of those keys and the backup of those keys somewhere else. Imported keys to KMS are not backed up by the AWS KMS domains. Native keys are backed up in a series of backups that we own. So we are in charge of the durability of our keys. You are in charge of the durability of imported keys. And it is for some of those reasons and more that I would recommend using the AWS KMS only path. It is the simplest to automate. It brings the robustness and performance and latency advantages of the fleet of HSMs managed by KMS. And it is the primary path that most customers take today. This is an interesting one because key rotation is very far and wide considered to be mandatory in encryption. And I can see why. Even from Roman times forward, the idea that you should move keys to improve security has always been there. But we have some rather provocative advice today, which is we don't think key rotation gives you any technical advantages in our system. So our guidance is if you are not specifically required to do so by compliance or regulatory mandates, don't use key rotation. If you are required to use it, consider using the automated key rotation that we've built that rotates keys yearly. It will make things relatively easy for you. And why do I say this? Why do I say rotation doesn't give you a lot of value in KMS? There are basically 3 reasons to rotate a key, and I think we've done a good job making 2 of them go away. One of the primary reasons you might want to rotate keys is the same reason you change keys in the real world. Imagine you're a landlord and you have many apartments, and Sarah in unit 3C leaves and doesn't give you back the keys. You're probably going to change the locks on that door. But notice that Sarah left with the keys, and that's the risk. In KMS, there is never a way to take keys out of our system. In fact, keys have never existed in a human-readable form. We have no APIs to read them. We have no APIs to export them. So this notion that what would I do if my keys could leak is dramatically reduced in the context of how we create and protect keys in KMS. We also have means in KMS to protect that landlord in ways that you can't do in the physical world. You could disable a key. A disabled key is essentially a destroyed key. It can never be used again. So if you had reasons to believe that a key was somehow in risk, you could use disable. You also have policies. Your landlord can't set a policy that says Sarah can never use that key again. In KMS, a key's usefulness requires both the existence of that key as well as permitted policies that allow the use of that key. So this notion of protecting against key leakage, if in some scenario you ever had a concern or a thought or a reason to believe that a key could leak, and again, there is very, 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 very hard ways for us to reason about how a key could leak. But even if you could reason about how a key could leak, you have policy mechanisms that you could deploy to simply prevent the use of that key from ever being used again. It would take us an hour or 2 to get into crypto wear out, but we'll go fast here. Keys can wear out. Just like a car key in your ignition system of your car. If you use a cryptographic key enough times, you will wear it out. NIST has some guidelines for this. In the way we use keys, and recall that our keys are used primarily as enveloping keys, and we bound the amount of data you can send to KMS at 4 kilobytes. And we use a key derivation function when we create our data keys. All of those different controls allow us to have a very large number of uses of this key before it can wear out. In short, you can invoke a KMS key in the range of 2 to the 60th operations before you would wear it out. Not that many people are that well commonly versed in what 2 to the 60th is, but it's a lot of API calls. It's in the tune of trillions a day for hundreds of years. And so we simply don't have any easy way to reason about a KMS key wearing out in any reasonable time frame, because no one is driving trillions of operations to a single key, trillions and trillions and trillions of times to the size of 2 to the 60th. So the short answer to crypto wear out is it would take you a very, very long time to wear out a KMS key. And these are the drivers for why we say rotation doesn't gain you much. It doesn't gain you much in blast radius protection, and it doesn't gain you much in crypto wear out. And yet, you may be faced with auditors or security teams or compliance or guidelines that say, I want to see rotation. And for those reasons, we've built a relatively easy key rotation in KMS for automatic yearly rotation. But I would avoid rotation as your first step. Moving on. We have this idea of encryption context as a way to create a bit of a locking mechanism inside the lock. What do I mean by that? Key encryption context is additional plain text data that you attach to ciphertext as a way, as a checksum, that only when this plain text data is presented will a decryption be authorized. So it's a way to fold into ciphertext additional timestamping and data that you want to provide as context. Maybe it's project data or time data. And you write that into your ciphertext. And it must be presented at decryption in order for valid decryptions to occur. So in some ways, you can think of this like a token or an authorization capability. It's a way for you to enhance the authorization of your decryption requests. One of the more meaningful places this is used, and it's used very richly across AWS services, is it helps against what in cryptography terms is called the confused deputy attack. It can also help you with some master data management. I gave the example of timestamps, for example. You might want to timestamp your data with encryption context that it has a time to live in it. And after that time to live, you wouldn't want to continue to use that ciphertext. So that's an example of using encryption context as authorizing the timestamp or time validity of data. My last recommendation in data protection is consider and take a look at Nitro Enclaves. Nitro Enclaves are part of our confidential computing strategy, and they are an isolated, hardened, highly constrained virtual machine. They allow you to build this protective compute environment that has very narrow, isolated interfaces that you control with an independent operating system kernel separate from the parent compute instance. For KMS, there's some very unique integrations we've built for the Nitro Enclave, such that we can encrypt data keys to the enclave, and only the enclave can open those data keys. So it's a way to run very confidential, isolated computing workloads and ensure that the KMS keys delivered to those workloads can never be opened or seen or accessed by any AWS operator or any entity in your organization not permitted to run the enclave. Similarly, for decryption requests, we use cryptographic attestation and digital signing from the enclave, so that when KMS runs a decrypt operation, we have high assurance that it came only from the Nitro Enclave because it is signed by an RSA private key that could only exist in the Nitro Enclave. The short of all of this is that Nitro Enclaves give you very protected confidential computing so that no instance administrator or AWS operator can access any of the code or any of the data ever running inside an enclave. Let's move on to performance best practices. For these, I have 4. I think the first thing to understand about data protection at AWS when you're thinking about performance is that different services have very different profiles when it comes to how many keys they need and how often they're going to need a key. Let's dig into that a little bit. For EBS volumes, EBS only needs 1 data key per volume. And once EBS loads a volume, it doesn't need that key again. So it needs the key to decrypt that volume. But once that volume is loaded, let's say into an EC2 or into an RDS instance, it is essentially all set. And so traffic from these services to KMS is quite infrequent. It can be in the order of 1 or 10 per day. And at the very far end of the other end of the spectrum is S3. You could imagine a large analytics workload or elastic MapReduce job in S3 that has billions of objects in it. In those instances, as well as in instances in Kinesis and SageMaker and other analytics tools, tools that operate on the vast scale of data lakes, we can see billions of requests to KMS because each of those objects has its own data key. It will have its own call to KMS. And so the first thing to understand about profiling performance for KMS is understanding that different services have very different orders of magnitude for how encryption works. To the left, we have EBS and RDS and other volume storage services, and there are going to be a handful of calls a day, or a month, or a year. It depends on how long those EBS volumes are loaded. To the right, we could have billions of operations per hour, and those are very large-scale data lake applications. So we go from a few a day to billions a day. We have essentially 7 orders of magnitude between our lowest callers and our highest callers to KMS. And in the middle, we could profile various services that are in the thousands. SNS and SQS, DynamoDB, Lambda, Secrets Manager would all be examples somewhere in the middle of those 7 orders of magnitude. And so I think the first thing to understand about profiling performance and performance characteristics is that there are different orders of magnitude in which services call KMS. The good news is KMS is built for the highest scale, and you don't actually have to reason too much about this. We are moving past the days when we had to throttle customers. Our throttling rates have been dropping by aggressive numbers every year, year over year. And today we routinely handle symmetric operations that reach 50 or 70,000 TPS per second. And so we have some very robust performance characteristics in KMS so that you don't really have to worry about the throughput of what your service is going to do for KMS. But one of the ways that you can improve at KMS, taking a look at S3 in particular, I mentioned earlier this idea that S3 can generate billions of calls to KMS. One of the significant improvements that you can make is to take a look at a new innovation in S3 called bucket keys. Recall that in general, every object in S3 needs a data key from KMS. And if every object in S3 needs a data key from KMS, if you have a billion objects, you have a billion calls to KMS. S3 created an optimization called bucket keys to change that relationship. Bucket keys shift the KMS traffic from each object now to each bucket. And S3 uses the bucket key as what we can consider to be an intermediate key. In some ways, people consider this a cache, but at a very strict technical level, this isn't a caching scheme. This is a key derivation scheme. S3 gets an intermediate key from KMS, and it uses a key derivation function, in this case, an HMAC, to generate and derive data keys for each object. This is a very nice balance because now we retain the property of unique data keys in each object. We retain the property of KMS security anchoring the system with HSMs and a strong root of trust. We retain the KMS key policies and KMS audit trail for data encryption requests. But S3 also has this tremendous optimization. By being able to derive data keys, the conversation between S3 and KMS can be reduced 10 to 10,000 times. So customers that have large workloads in S3 get great advantages here. They get performance advantages, latency advantages, and perhaps most significantly, they get tremendous cost savings. Because now, for large workloads, instead of 1,000 or 1,000,000 or 1 billion API calls to KMS, they have that reduced 1,000 times or 100 times because the interaction at the bucket level is vastly less than the interaction at the object level. Sometimes people ask us to dive deep here and say, what will my savings be and how can I reason about my savings? And it's a reasonable question. The answer to that question can be quite complex. It will depend on how frequently you write new objects next to each other. It will depend on some of the caching of the bucket key. Each bucket key is refreshed every 5 minutes. Obviously, it will depend on how many objects you store in an individual bucket. The more objects you store in one bucket, the more this efficiency pays returns. Moving on, That same notion of efficiency and savings can be deployed in our client tools. We offer an encryption SDK, the shorthand of which is the ESDK, for customers who want to write cryptographic applications of their own. We call this client-side encryption, and we contrast it with the embedded data protection that I've been talking about the rest of this presentation. So in addition to your ability to use data protection inside AWS services, you can use data protection in your own client apps. The ESDK is our recommended AWS-sponsored tooling for that. And data caching inside the ESDK can help you with performance and cost savings. So for those customers looking at the ESDK, I would encourage you to look at data key caching as a way to improve the efficiency, performance, and cost savings of client-side applications, somewhat equivalent to the efficiency and cost savings brought by bucket keys. Last but not least, as I mentioned earlier, last year we launched a new feature in KMS called multi-region keys. Multi-region keys allow you to create a key in one region and copy that key material with identical KMS key IDs into other regions. A very powerful use case for these multi-region keys is for customers that need to write and read data across DynamoDB global tables. And so the challenge here is, how do I protect records in a DynamoDB global table with very narrow client-side encryption using the Dynamo database encryption client? This can be hard. Without using multi-region keys, it can be painful to make cross-region calls. These could be very high latency calls that you wouldn't want to use in a global tables environment. And it can be hard to know how to wrap different keys to different envelopes. So if you weren't going to use multi-region keys, you would have to create a scheme where you had multiple envelopes with multiple keys inside them, and it could be quite cumbersome to build. A better answer for DynamoDB global tables is to take a look at multi-region keys. This allows you to copy the same key into multiple regions and avoids those complex issues around cross-region calls or the need to wrap in multiple envelopes. It really is quite an elegant architecture because it removes the need to decrypt and re-encrypt when replicating that data across tables. In my last section, I want to briefly go over some KMS policy best practices. These are ways to tighten and improve the authorization of when and how keys get used. I think the first and most easiest recommendation is to consider enforcing a separation of duties in KMS. Use your IAM policies and KMS key policies to think about different personas that perform different types of key management tasks. Set up a set of roles for IT security. These are the people that access and manage key policies. These are the sort of guardians of the henhouse, if you will. They dictate when the doors can be opened and how many hens can be visited, and they set key policies. But notice they're not using keys. They don't need to read and write keys. They're the security guards. So they shouldn't have key usage, because that's sort of mixing metaphors, if you will. The guards don't need to be using the keys. And so create separate roles for key users. Key users should have permissions and policies that define how they use keys, but those users should not be permitted to write policies. Again, the opposite is true. People that use keys don't necessarily need rights to define the policies for how to use keys. This is a nice, clean separation of duties. It's a best practices across whether you're building firewalls or email security or data protection. And KMS offers a pretty easy way to think about, and we have some guidance in our documentation for how to think about the separation of duties in KMS. But I would say that's, if you do nothing else in your policy management, deploy separation of duties to isolate roles and permissions for key management, separate than roles and permissions for key usage. Moving on to some more sophisticated tools, we've launched the ability to support attribute-based access controls in KMS key policies. This follows on to the attribute-based access control launched in IAM. Now you can take that same tag-based approach where you tag projects or tag users or tag resources, and those tags can flow all the way through a decision. You could imagine a blue team with blue resources getting permission to only blue keys. In this ability, tagging allows you to build more dynamism and more flexibility so that you don't have to harden your key policies to specific ARNs or specific roles, and it allows you a layer of abstraction that makes provisioning and managing policies easier at scale. In a separate vein, in addition to attribute-based access control, we also offer VPC endpoint policies to lock down keys from the network context. Think of this as policy control for where you can access keys. This is an important protective mechanism against insider risk. This lets you set up essentially rules around the context of where the request is coming from. What was the source IP? What time of day was it? Was this person authenticated with MFA? Were they coming from a certain service? What was their principal organization? So this is the VPC context for where did a request come from. So in addition to IAM policies that really govern who is trying to access a key, and KMS policies that really govern the types of actions you can do on a key. So those are the who and what. This is from where policies. So it's an additional filter, an additional layer of control that we launched 2 years ago to help you better tighten key control. One more level of filtering and granularity of control are service control policies. If VPC endpoint policies were adjacent to IAM and KMS policies, meaning user context in IAM, KMS key resource context in KMS policies, VPC and network context in VPC policies, service control policies are at a higher layer. In plain English, they allow you to drive the permission at the service or organizational level of your business. You could set an SEP, for example, to only permit access in 2 regions. That would be an example of a service control policy that sits at a higher level than the other policy frameworks that I've already discussed. My closing thoughts. I think data protection has come a long way since KMS launched in 2014. In fact, I found out the other day that we used to throttle higher than 700 TPS. And so we are now approaching more than 2.5 orders of magnitude of performance scale out in that time frame. So we are hundreds of times bigger and broader than we were in the beginning. And that makes sense. You know, when we launched, there were probably just a handful of services that could talk to KMS. SNS, SQS, S3 were some of the very earliest services that communicated with KMS. Now we are the default data protection path and supported in 103 services. We're working on increasing degrees of automation so that you can automate your use of data protection through CloudFormation, AWS Config, and other tools. And we're seeing more services turn on the easy button so that you can have automatic encryption, encryption by default. If you don't do anything else, encryption shows up free and easy. We've also built a high degree of trust and certification into these locks and keys. We work very hard on our security attestations and SOC controls and FIPS certifications. We are moving to a new FIPS 140 Security Level 3 certification expected back from NIST this year. We are in the halfway through that process with a testing lab. We've been approved for FIPS Security Level 3, and we expect an answer from NIST shortly. You can check that status on the NIST FIPS 140 website. And we also continue to work through different certification programs globally around ISO, STAR, PCI, FedRAMP, and so forth. And last but not least, and I think as you saw from our VPC and attribute-based access control discussions today, we continue to hone in on and create very robust and fine-grained policies that govern how you use these keys. And again, I'll repeat something I said earlier. Cryptographic locks and keys are great, but you also have to make sure you have an accurate understanding of the permission model for when and how keys get used to ensure that they stay secure. There's a lot more content on how encryption works, hosted by Ken Beer. This is almost the foundational walkthrough of a deep dive in KMS. If you are curious about confidential computing, Mark Ryland gives a very detailed security benefits overview of the Nitro architecture that I spoke briefly about today. And if you're curious about some of those bigger projects and analytic workloads, strategies for data lakes, Raghu does an overview of all of that in a presentation provided here. And last but not least, KMS best practices that I touched on. Peter does an entirely dedicated 1 hour with some additional tips and more explanation on audit than I was able to cover today. And with that, I think we're out of time. I want to thank you for attending today, and good luck in your journey to the cloud. Thank you very much.